Hello, I'm Vaishali. Welcome you all to my channel. So today I'm starting with the complex analysis video. In this video, we will discuss the analytic function. We will discuss this topic, analytic function of the complex variable. When we say a function is analytic, okay, so that we'll discuss today, this one. So first topic we will discuss today in this video, analytic function. If there is a given function to you, and then you have to check whether the function is analytic or not. If it is analytic, how you can say it is an analytic in a full region, or it is analytic in a single point. So that we will understand with the help of the definition and its theorem. We have two theorems based on analyticity of a complex variable. First is the necessary theorem and other is the sufficient theorem. So what is the analyticity of a function in a complex variable? Is actually we will check the function is differentiable or not. Okay, so this is related to a differentiability of a complex variable. Okay, so now moving directly to the topic, and then I'll explain you. If you feel the videos are helpful for you, so please subscribe to my channel, which is really helpful for me to be motivating from your side. And please pour your feedback, either be the good or be the bad, in a comment section below, which help me to improve myself. So this is my I want from your side to subscribe my channel. Okay, so let's start for the topic of analyticity of a complex function. See, I just tell you a few things which is required to be known before the analyticity of a function. Z is a complex variable which is represented in the form of x and iy. We used to write it z is equals to x plus iy. Fz, which is function of z, is also be represented as w. W is equals to fz is a function of u and v, where u is a function of xy plus I, v is a function of xy. So we used to write w is equals to u plus iv, okay, like this. Now, I hope this is enough to know. Yes, the point. When we call a function is a single valued and multi-valued. When we put for a given region, if we give different values of z to a function, and we will get different values of a function for a different values of z. So that function is called as multi-valued because it is getting multi-value, different values for different values of z. When we'll give different values of z and we are getting a unique value of a function, that function is called as a single valued function in a given region. Okay. So now coming directly to the definition. In this video, I'll explain you the definition, then two theorems, the necessary condition, the sufficient condition, and based on that, we'll do 3 questions. Okay. So now I'll explain you first the definition. Let function fz be a single valued function. If a function is a single valued function defined in a given domain, let this be a domain and the function is getting the unique value for all the values of the z. If the function, then the function is said to be analytic at a point, at a particular point. Inside the domain, there is a point z0, and we will say at this particular point, the function is analytic. Okay, the domain, and inside the domain there is a point z0, and we'll say the function is analytic at a point z0. It means the function is differentiable at z0 and also differentiable in the neighborhood of z0. Okay, in the neighborhood of z0. Then we'll say the function is analytic at a point z0. At a point z0 of D, if it is differentiable not only at z0 but also in the some neighborhood points of z0. Okay. Now next, when we say the function is analytic in a full domain, it means a single valued function which is differentiable at each point of a domain, means it is differentiable in a full domain. At every point of a domain it is differentiable. Then we'll say the function is analytic in a domain D. Now the question arises in the mind, if the function is analytic in a full domain, it is analytic. Okay, it is differentiable in all points, then we'll say it is analytic in a domain. If it is differentiable only at z0, not the nearby neighborhoods, then what we'll say? We'll say the function is not analytic. We'll say the function is not analytic. I'll write, we'll say the function is not analytic, but function is differentiable. Okay, we'll say this thing because we get only a single point, and analyticity is not a point property, but differentiability is a point property. Okay, the function which is analytic, now the third line, the function which is analytic is also called as holomorphic function. Okay, so either the holomorphic or the analytic, they follows the same concept. Now moving to the first theorem. The first theorem is the necessary condition of a function to be analytic. Okay, so what we'll come to know about, what we'll understand in this theorem. So when we'll say about the function to be analytic, okay, so for that, in its necessary condition, we should have a given function. The function should be differentiable at a point, and the partial derivatives of a function should exist, and it should satisfy the CR equation. Okay, so I'll just read the statement of the theorem first, and then I'll explain you the proof. Okay, this is the statement. If a function fz which is equals to u plus iv, if a function fz u plus iv is differentiable at any point z, the partial derivatives of u and v with respect of x and y should exist and satisfy this condition. Ux is equals to vy. This is very important. I am putting the star. Ux is equals to vy and uy is equals to minus vx. See, fz, I told you fz can be written in the form of u and v. U plus I v. So u is a function of xy and v is a function of xy. So we can find partial derivatives of u with respect of x. So this is ux. Partial derivative of u with respect of y, which is uy. Partial derivative of v with respect of y and x, which is equals to vx and vy. So when these exist and it's satisfy the equation, it satisfy the condition, which is ux is equals to vy and uy is equals to minus vx. So these are called as the CR equation. Then we say the function is analytic. Okay, this is the necessary condition. This is also called as Cauchy Riemann equations. And in exam sometime they give you to prove the Cauchy Riemann equation. So you have to do what I am explaining you. Now I'll just erase it all and then I'll explain you the proof. So what all will be going to use and what we have to prove, that I'll explain you. So first we'll take the function is differentiable, okay, and we will prove that ux, uy, vx, vy exist, and we'll show the condition exists. How the condition exists, that will show. So per proof, we'll first take that fz which is equals to u plus iv and z is equals to x plus iy. So the small shift here, small increment in a z value will become delta z is equals to delta x plus I delta y. We'll take these things. This is the function, this is the variable z, and this is the small increment in the value of the z. Now we know the function is differentiable at a point z. So the same it is written here. See, let w is equals to fz is equals to u plus iv. We have z is equals to x plus iy and delta z as this. Since the function is differentiable, we'll be using this condition that the function is differentiable at any point z. So then we'll write, how we'll write, I hope you know the function, I hope you know what is the definition of differentiability, how we'll write the function when it is differentiable. I'll just tell you. Limit delta z tends to 0, okay, del f upon del z, which is equals to f z plus del z minus fz upon del z, bracket close. Here also limit del z tends to 0. Okay, now limit del z tends to 0 can be written as del x plus I del y tends to 0, and here del f upon del z, which is equals to limit del x plus I del y tends to 0. Inside this I told you that fz is equals to u plus iv. Then what is f z plus delta z? Can we write it like this? U x plus delta x comma y plus delta y plus I v x plus delta x comma y plus delta y. Can I write it like this? Value of fz and value of fz plus delta z. Now I'll put these values here in this first first value, fz plus delta z. So I'll write it u1 this plus iv minus u plus iv. Okay, inside this I'll write u xy plus I v x y. So I hope you will get this thing directly. See here, you will get this thing directly. Sorry, you will get this thing directly. Limit delta z tends to 0, u x plus delta x comma y plus delta y minus u x y upon delta x plus I delta y, and plus I v x plus delta x comma y plus delta y minus v x y upon delta x plus I delta y. Now if we say a function is differentiable, it means it should possess a unique value. Okay, so that we'll check through different path. It means first we'll take two conditions here. First we'll put delta y tends to 0, it means function will be in terms of x. Then second we'll put delta x tends to 0, then the function will be in terms of y. Then we'll see whether those values will be equal or not. As we know the function is differentiable, then we'll assume the value should be equal. If the value should be equal, then we'll say what will be the outcome. I hope this is clear. So this concept I am using here. See now, see this thing. Now taking del z to be wholly real, okay, that means del y tends to 0. If del y tends to 0, in this first part, this will be 0, okay, this will be 0, here this will be 0, this will be 0, and this will be 0. Now if you see the this particular equation will be converted to ux plus del x comma y minus uxy upon del x. What is this? This is the partial derivative of u with respect of x. Can I write it like this? Del u upon del x. Similarly, if you see this thing, similarly, I'll just erase it. Similarly, if you see this thing, this will be del u upon del v upon del x, and this will be del u upon del x. So we have written the same thing, del u upon del x plus I del v upon del x, which is ux plus I vx. Now second condition we'll be using, that delta x tends to 0. When delta x tends to 0, come here, this will be 0, this will be 0, then this part will be 0, this part will be 0. So if you'll see ux comma y plus delta y minus uxy upon I del y. So what is this? We'll write del u upon del y with I plus I del v upon I del y. I and I will be cancelled. Here it is I, so we'll rationalize, we'll multiply both the side numerator and denominator with I. It will become I del u with a minus sign upon del y, and it will become plus del v upon del y. Okay, come here, the same we'll get it here. See, minus del u upon del y with I and plus del v upon del y. They have written it like this, vy, okay, minus I uy du y. Okay, so this is the second which we obtain when we put del x tends to 0, and this is the first one which we obtain when we put del y tends to 0. So as the function is differentiable, we can equate these both values. Okay, so since the limit is given by limit del tends to 0, del f upon del z is unique, so we should equate these things. After equating these things, we will get ux plus I vx is equals to vy minus I minus I uy. So now equating the values of real and imaginary part, so ux is equals to vy and vx is equals to minus uy. So we got these two conditions, and these two equations or the conditions is called as Cauchy Riemann equation or the CR equation. Okay, so here proof finished. Now we'll move to the next, which is the sufficient condition of the function to be analytic. So I have only written the theorem because this theorem will use in the question to prove the function is analytic. So understand this very clearly. The single valued continuous function fz, function is continuous and single value, is analytic in a domain if the four partial derivatives ux, vx, uy, vy exist, are continuous. The partial derivative exists and they should be continuous, and they satisfy the CR equation at each point of D. Which point is asked, they have to satisfy CR equation in that point. Okay, so for the function, if like in these three, I'll be discussing these three questions. In these three questions, the function is given to you. Okay, so if you have to prove the function is analytic, what we'll be using, we have to first find the partial derivatives with respect of u, x, uy, vx, vy. We have to check the partial derivative exist. We have to check the partial derivatives are continuous, and then we have to show the CR equation satisfy at that point which is asked or not. Okay, at that point CR equation satisfy or not. If it is, then we'll say the function is analytic. Now moving directly to the question. So we'll do all the three questions. I have written one by one so that I can discuss with you very clearly. So here, this is the question number first. So if you feel the videos are helping you, so please subscribe to my channel. Okay, so the that red bell is given near to a, the black bell is given near to a subscribe option. Press that also. Whenever the new videos will be coming to my channel, that will be pop up in your account. Show that the function is this is an, just put my image down. Okay, show that the function this ex cos y plus I sin y is an analytic function. This function is analytic function. We have to show that, and then we have to find the derivative. Now I'm writing here. Now see this question very clearly. Fz is equals to e to the power x cos y plus I sin y. Okay. Now ex cos y plus I ex sin y. This is fz. So we'll write fz in the form of u plus iv. This is u and this is v. So we have to show the function is analytic. That means you have to find the partial derivative of u with respect of x. Then we have to find the partial derivative with respect of y. So I am doing the same, del u upon del x, which is also written as ux. So I am derivating this with respect of x. Okay, partially. So I'll get e to the power x cos y. Then ui, which is equals to del u upon del y, which is now u with respect of y. So e to the power will be same, e to the power x, cos y will be changed to sin y and with a minus sign. Then v, which is equals to e to the power x sin y, will differentiating v with respect of x, which is del v upon del x, which is e to the power x sin y, will get this. Then vy, which is del v upon del y, which is e to the power x sin y, is changed to cos y. Okay, partial derivative exist, they are continuous. So here you should also know which functions are continuous. As we get ux, vy, vx, vy in terms of exponential and trigonometric values, exponential values, polynomials and a constant function are continuous in nature. So here the partial derivative exists and they are continuous. Okay, so first condition satisfied. Moving to the second condition, which is that we have to show that they are satisfying CR equation. Okay, so now I am proving the second part here. What are the CR equation? Ux is equals to vy and uy is equals to minus vx. Now put the value of ux. Ux is equals to e to the power x cos y and vy is equals to e to the power x cos y. It is satisfied. Then uy is equals to minus e to the power x sin y, which is equals to minus vx is e to the power x sin y. So this is also satisfied. What we will say? We will say the function is analytic in a given region. In a full region, this function fz is analytic. Now they have asked you to find the value of the derivative f dash z. Okay, which we also write it like this, del f upon del z. And here I am partially derivating it with respect of x. So del f upon del x I am finding. Okay, which is f dash z. So f dash z is ux plus ivy. Okay, now put the value of ux. Ux is e to the power x cos y plus ivy is vx. It is vx. Ux plus ivx, because we are derivating it with respect of x, so partially to find the value of derivative. So ex cos y plus ivx is e to the power x sin y. So take e to the power x common, we will get cos y plus I sin y. Now cos y plus I sin y is again e to the power iy. I hope you know the formula. It is e to the power iy. X plus iy, can we write it like this? E to the power x plus iy, and you know that it is e to the power z. Now f dash z is equals to e to the power z. This is your final answer. So here we have shown that function is analytic, and then we have shown the value of a derivative. I hope this question is clear. So moving to the next question. See, these all questions are very important questions. Okay, don't think that these are very easy question, because these types of the question usually comes in your CSIR NET and your GATE exams also. They don't ask very difficult, they ask from your basics. So please work on these concepts, and from your university book do some more same types of the question which I am explaining you here, so that you will be having the more practice. Or if you are preparing for competition exams, then go through the PYQs related to this analyticity concept. Okay, and if you have any doubt, then ask from me in the comment section below. Find the point. This is different question. Find the point where the CR equation are satisfied for the given function. Here it is saying in the question that function is given to us, which is fz is equals to xy square plus I x square y. This is the given function. They are saying that this function is already analytic. It is satisfying. No. So this is the given function, and they are saying that this function is satisfying the CR equation. Okay, and we have to find the point where it is satisfying. It means that the partial derivative exists. It means that it is satisfying the CR equation. So these 2 points will take under consideration, and we will start proving it. So this is the u and this is v. This is u and this is v. Now find the ux, which is equals to y square, uy, which is equals to 2xy. Now vx, which is equals to 2xy, vy, which is equals to x square. Now as it is satisfying the CR equation, so ux is equals to vy and uy is equals to minus vx. Now y square is equals to x square. We does not get anything related to the particular point where it is satisfying. Okay, so we only get an equation y square is equals to x square. Name it as 1. Now from the second condition, first condition, second condition, from second condition what we will say? We will say ui is 2xy which is equals to minus times of vx which is equals to 2xy. Now taking 2xy to the same side, we'll get 4xy which is equals to 0. 4 is not equals to 0, of course, so what we'll take? Xy is equals to 0. It means when xy will become 0, either x is equals to 0 or y is equals to 0, or both x and y is equals to 0. So if we see the first condition, it says y is equals to x square. If we remove a square from both the sides, we'll say the value of x and y is equal. If the value of x and y is equal, it means that this CR equation will be satisfied when both x equals to 0 and y equals to 0. Okay, so we will take only this under consideration, that x is equals to 0 and y is equals to 0. We cannot take either x is 0 or y is 0. We will not take this condition. Okay, it implies that function is differentiable at origin, because we will getting the origin point and partial derivative exists and the function is differentiable at the origin, and I'll explain you here also this thing. Okay, so we got the point where the CR equation satisfied. We say CR equation satisfied at the origin. This I hope till here first part is clear, where the point where it is satisfied at the origin. Now moving to the second part of the question, find the derivative and check whether derivative exists or not. So del f upon del x which is equals to f dash which is equals to ux plus I vx, will put it value ux is equals to y square plus I vx is equals to 2xy. Now we know the CR equation is satisfying at the origin, where x and y is equals to 0, 0. Put these values, we will get the finite value of the function f dash. So we say the function derivative exists at the origin. I hope this is clear. Now moving to the third part. Now they have asked where the function is analytic. See, in this full given region, let this full given region is given to you. It is saying that x and y satisfying the CR equation only at the origin point. If we go to the nearby neighborhood points of the origin, we does not get the function values exist. Okay, because we are not having any point in the hand, we have only the origin point. So we say the function is not analytic. Function is not analytic, but function is differentiable at a point. As I already told you, the differentiability is a point concept while analyticity is a domain concept. If the function is analytic in the neighborhood points of origin, then we'll say the function is analytic at the origin. Okay, but here it is analytic only at a particular point origin, so we can't say that the function is analytic. I hope this is clear. Moving to the next question. See, this question is totally different. Find the value of C1. Find the value of C1 and C2, the arbitrary constant, such that the function, this is the given function, is analytic. So here the function is given to you that the function is analytic. I'll just write the function fz is equals to x square plus c1 y square minus 2xy plus I c2 x square minus, put the bracket, minus y square plus 2xy. This is the function. So this is u and this portion is v. They have given you the function is analytic and we have to find the value of c1 and c2. So what we'll do, we'll find the partial derivative. We equate it with the help of the CR equation and then we will check what is the value of c1 and c2. So ux is equals to 2x, that means derivative of u with respect of x, which is equals to 2x plus c1 y square is 0 minus 2y. Then uy is equals to 2 c1y minus 2x. Then vx is equals to, from here, 2x c2, that is v with respect of x I am differentiating. So 2x c2, okay, then 2x c2, then this will be 0, then plus 2y. Then vy, which is equals to minus 2y, this one I am differentiating this, minus 2y plus 2x. Now CR equations, we'll put the value in CR equation. ux is equals to vy and uy is equals to minus vx. So put the value ux is equals to 2x minus 2y, which is equals to vy which is equals to minus 2y plus 2x. So this is satisfied, but we does not get the value of c1 and c2 from here. Now moving to the second condition, this is the first condition, this is the second condition. Uy is your 2c1, I am putting here in the second condition, 2c1y minus 2x, which is equals to minus of, we have to put uy is equals to minus vx, vx is 2x c2 plus 2y. Now see, we have only one equation and we have two constraints, so what we'll do, we'll equate the coefficients of x and y to get the value of c1 and c2. Okay, so I am doing it here, equating the coefficient of y first. Okay, both the side, left side and right side, we'll get 2c1 and minus 2, so equal to, we'll get c1 equal to minus 1. Then equating the coefficient of x, minus 2, which is equals to minus 2c2, so c2 is equals to 1. So c1 is equals to minus 1 and c2 is equals to 1. Now we'll get a new function where we'll get the value c1 is equals to minus 1, c2 is equals to 1. When we put these values in this given function, we'll get a new function fz. Okay, so first part of the question is done. Now they have asked what is the value of f dash z. Now I am finding the value of f with respect of x, which is del f upon del x, which is f dash. Okay, so ux, it is here x minus, I just write it the value 2x minus 2y plus I, vx is 2x c2, c2 is 1, so 2x plus 2y. Now it will become 2x minus 2y plus I, 2x plus I 2y. Now we have to write this function in the terms of z, so write the values in the terms of z. How? Like, see there, 2x plus I 2y, 2x plus I 2y plus, I am taking this and this together, 2x plus I 2y, then these two together. See, I 2x minus 2y. So 2x plus 2y, I can write it like this, 2z, because if you remember, x plus iy is equals to z, but ix minus y is equals to iz. Okay, so I am writing it here, plus I2z. Not taking 2z common, I'll get 1 plus I. So this is the answer of a derivative f dash. Okay, so here we finish the third question. If you have any doubt related to more questions of analyticity, then please comment that in a comment section below, and please subscribe to my channel and share my videos with your classmates if you want more such videos on complex analysis. Till then, goodbye and take care, and thanks for watching my videos.